When two wave-like objects approach each other, they often appear to be physically resisting. They distort and fluctuate as if pushing against an invisible barrier. In a classical system, we describe this as a force, a dynamic push between two distinct entities. But at the quantum scale, the mechanics are driven by a different set of rules. This behavior is central to the problem of identical particles. Physicist Wolfgang Pauli demonstrated that the state of the entire system is governed by a strict requirement of exchange symmetry. In a system of fermions, like electrons, the collective wave function must be anti-symmetric. If you were to swap the coordinate labels of two particles, the mathematical sign of the entire system would have to flip. This isn't just an abstract rule, it alters the physical distance between particles. When we calculate the expected square distance between two fermions, the anti-symmetry requirement generates a specific interference term at the end of the equation. Because of its mathematical sign, this term forces an increase in the expected distance between the two particles whenever their wave functions overlap. This creates a low-density region in position space, known as an exchange hole. Since the electrons are maintained at a greater distance, the energy associated with their mutual Coulomb repulsion is lower than for distinguishable particles. There is no force carrier here. No photon is exchanged to mediate this separation. It is a strict geometric constraint born from symmetry, an example of how spatial geometry can successfully masquerade as a fundamental force. Mapping the continuous spatial geometry of every overlapping electron in a solid is computationally impossible. To understand materials at a macro scale, we need a way to translate these spatial constraints into the observable behavior of electron spins. In 1926, Werner Heisenberg began mapping how this spatial exchange symmetry could be used to explain the magnetic properties of matter. Paul Dirac simultaneously realized that the system could be simplified. Instead of calculating the exact spatial curvature of the exchange hole, the interaction could be treated as if the spins of the particles were directly coupled together. This led to the Heisenberg-Dirac Hamiltonian. It removes the continuous spatial coordinates entirely, leaving only the spin-angular momenta of the particles. The complex spatial repulsion is compressed into a single variable, the exchange constant, JAB. When this constant is positive, parallel spins are energetically favored. When it is negative, the math favors an antiparallel alignment. When this localized alignment occurs across billions of atoms in a crystal lattice, we observe the macroscopic effect of ferromagnetism. By replacing continuous spatial dynamics with a localized point operator, Dirac and Heisenberg established the first functional template for an effective field theory. We can scale this concept up from atomic orbitals to high-energy scattering environments. Consider a Yukawa model containing a massless interacting fermion, psi, and a massive scalar field, phi, with a mass defined as m. These diagrams illustrate the scattering process. Two fermions approach, interact by exchanging a scalar particle, and scatter away. The exchange is defined by the propagator equation. Here, p is the momentum of the colliding fermions, and m is the scalar field's mass. If the energy of the colliding fermions is significantly lower than the mass m, the heavy scalar cannot be produced on shell. It remains a virtual state, and its specific dynamics decouple from the low-energy observables. This low-energy limit simplifies the math. Because the mass m is much greater than momentum p, we integrate the heavy field out. By performing a Taylor expansion on the denominator, we isolate the leading order behavior of the interaction. At these scales, the ratio of momentum to mass is negligible. We can drop the term entirely without losing accuracy at low energies. The complex energetic exchange collapses into a single static value. Visually, the internal exchange line in our diagram shrinks to zero. The interaction is now modeled as a single 4-fermion contact point. This defines our effective Lagrangian, an equation containing only the light fermion fields we actually observe. The heavy scale information hasn't been lost. It is stored within the coefficient c, where c equals the square of the coupling divided by the square of the heavy mass. The heavy physics has decoupled. We have replaced a complex ultraviolet amplitude with a simple dimension 6 operator that accurately describes the physics at our available energy scales. Calculating real physics requires going beyond these simple tree-level snapshots. When we account for quantum loops, internal momenta can mathematically run to infinity. Without a systematic approach, these infinities make the theory uncalculable. Yet precision can be achieved without knowing everything. Julian Schwinger calculated the anomalous magnetic moment of the electron by focusing only on QED, ignoring the massive weak force gauge bosons that were entirely unknown at the time. Modern effective field theory manages these complexities by strictly separating the calculation into two phases, matching and running. During matching, we equate the full theory with the effective theory at the mass threshold of the heavy particle. This determines the values of our coefficients. Then, in the running phase, we use renormalization group equations to scale those parameters down to the level of our experiment, isolating the physical logarithms. By utilizing dimensional regularization, the heavy scale unknowns are sequestered into matching coefficients, leaving the low-energy physics internally consistent. This process is the primary way we investigate the limits of the Standard Model today. We know the Standard Model is an incomplete description of high-energy physics, but as we reach the technological limits of our particle colliders, we cannot always produce new particles directly. Effective field theories allow us to search for beyond Standard Model physics indirectly. We don't need to see the particle to see its effect on the math. We augment the Standard Model by adding an infinite tower of higher dimensional operators, each representing a possible interaction at higher energies. Just as the Heisenberg Hamiltonian modeled the macro effects of magnetism, modern EFT provides a framework to map the low-energy consequences of physics occurring at scales far beyond our current reach. To find these signs, we look at the most accurate data we have, the precision electroweak measurements. These are the S and T operators. They are used to constrain new theories by analyzing modifications to gauge bosons. We hypothesize a new heavy particle, like a scalar triplet, and model its effect through a virtual quantum loop. When we integrate that particle out, the loop collapses. The information regarding that particle's mass and its coupling is absorbed into the coefficients of the S and T operators. By comparing experimental data against these coefficients, we can set mathematical boundaries on the mass and coupling of particles we haven't even discovered yet. We do not always need to reach higher energies to observe the universe. We only need to decode the precise geometric constraints that the high-energy world imprints on our own.